So if we all knew the IP address that we wanted to connect to at any given moment, we could just enter the IP address and make our connection. Fortunately, we don't have to remember the IP address of every device, especially with IPv6, which are very, very long addresses. DNS comes to the rescue with providing a directory type function with respect to translating text host names or email addresses, or really any kind of reachability information, handles, what have you, into IP addresses. Now the information in DNS is really organized into a domain tree, and if we look at the root of the domain tree, the internet root, it's typically represented as dot. So this is really the root of the tree, and then below that you have your TLDs, your top-level domains, so the familiar .net, .com, certainly .edu, .gov, and then there's also other types of TLDs, country code TLDs, for example, .us, .uk, and so forth. So there are numerous TLDs, and more coming. Actually, as we speak, there's a process to expand the top-level domains that are going to be made available for use on the internet. So as an organization, let's say I want to get a .com domain, and so what I would do is I would, basically register or attempt to contract with VeriSign, who happens to administer the .com domain, and I would like to get the example.com domain for, let's say, for the sake of this example. And so I would contract with them to subscribe for that domain, and let's say I was successful in obtaining that. So now, having gotten that .com says that, okay, anything with ending in example.com in a domain name, I'm going to send to you. So make sure that you can answer all the questions that come for example.com. So much like the address space being kind of carved out and given as your kind of piece of the pie for you to carve out, it similarly works with DNS. So within my little piece of the pie here, my example.com, I can now define host names that I want to give for my web server, for example, my mail server, my individual internet reachable hosts, for example, for devices that I want to provide reachability for. But I can also define my own subdomains, so tech.example.com, just to maybe organize my namespace a little better. If I get if there's an internet query for something tech.example.com, well, the com server is just going to say, okay, well, you have everything example.com, so you figure it out. Same thing works if I want to actually delegate a subdomain. So let's say I have an engineering group in my company. They want to run their own DNS server and just be responsible for that and not have me worry about it. So I can actually delegate a sub-portion of my namespace to another organization, much like .com did to me. So it said to me, everything in example.com is your responsibility. I'm going to send everything to you. I can say that to the eng team here. I can say, okay, fine. Everything ending in eng.example.com, I'm going to send to you, and you're responsible for resolving all that. Any subdomains below you, any hosts in your domain. So here I've got labbox.eng.example.com, for example. So .com is going to see, oh, it ends in example.com. I'm going to refer them to you and example.com, and I'm going to say, well, okay, I've delegated that further to eng.example.com, and I'm going to refer the querier to that domain server, which is going to resolve that information. So the structure of the information in DNS really relates to how where to find information that you're looking for from a query. So when you type in a web address, that dictates, in essence, the structure of the information you're looking for by virtue of how it's organized in the domain tree. And you can basically utilize that through the referral process, as we'll look at next, to locate who has that information and then to finally get the answer. So the domain administrator publishes that information in the form of DNS resource records. So that's in essence for labbox.eng.example.com. My eng.example.com administrator has published a record in there to say the IP address of that server is 192.0.2.54, for example. So they can publish that information, and I don't need to worry about it as the administrator for example.com again, because I'm going to send everything with eng.example.com to them. I don't need to worry about anything in that subdomain or that portion of the domain tree. I've delegated that, and I'm going to refer to that. And they can further subdivide if they want to as well. if they wanted to set up, tech.eng.example.com and delegate that to yet another administrator, they could do that. But certainly as you get longer and longer domain names, it could become more difficult to remember, which is really the purpose of DNS, is to make it simpler to navigate by name. So I talked about the structure of the information, and I mentioned referrals, but how does that actually work from a DNS server perspective? So typically, when I connect my laptop to the network, I get an IP address, let's say through DHCP, either from my service provider or my enterprise IT group has set up a DHCP server. Along with that DHCP address, I might also get the name of a DNS server to query. So if I'm in my home office, I might get one DNS server to query. If I'm at home, I get a different, the service provider DNS server that I should query. So this auto configuration through DHCP enables me to get an IP address that enables me to be configured with efficient information to say, okay, this DNS server is relevant to where you're connected to the network right now, so issue your queries to that DNS server. So having been so configured, without me even having to know anything, I just plugged in my laptop, and lo and behold, this all happens behind the scenes, which is all a good thing. So that IP address that I get provisioned with through DHCP is what we call a recursive DNS server. And the reason we call it that is because it's actually going to now iterate on my question that I'm asking it, and it's going to then iterate or recursively attempt to locate that information. And what it's looking for is an authoritative DNS server which has the information. It's authoritative for that portion of the domain tree, and it should have the information that I'm looking for. And where do I start? If I don't know where example.com is, I'm going to go up to the root server. So there's a set of DNS servers that serve the internet root, and they don't have the information about www.example.com. However, they know where the .com, the .net, the .org, all the TLD DNS servers are. So they know the next layer down. So they're going to basically give me a referral to say, okay, well, here's where the .com server is. So my recursive server is then going to take that and issue another query, another iterative query, which is a kind of a discrete query. But I'm going to pack in multiple iterative queries to be able to recurse on that. So having gotten the IP address of the .com server from the root, I now issue a query to the .com server. It too, remember, it just gave me the example.com domain and said, well, look, I'm going to send everything to you. I don't care what your www address is. I'm just going to let you answer that. So it's also going to answer with a referral to say, okay, well, here's where the example.com DNS servers are. As part of their domain registration, they had to give me the address of a couple DNS servers. So here they are. And so now with that information, my recursive DNS server can attempt to contact those DNS servers. And here's where basically I finally get to the example.com DNS server. It responds with my answer, with the IP address. I actually cache that information so that if somebody else 10 minutes later asks me the same question, I don't have to go through this tree process again. I have the information in cache, and I can just provide the answer 192.0.2.54. And once I get my answer on my laptop, I'm now done with DNS, and I say, okay, I'm going to now connect. I'm going to now make that connection over through my ISP and issue a destination IP address in my IP packet with a 192.0.2.54. And so it's going to be routed in that way, however this network is subnetted on a CIDR basis. Let's say it's 192.0.2/23, and based on those 23 bits, it'll be routed to the destination ISP, and then that ISP will locate it accordingly. So in that manner, DNS really provides that hook from a name into the IP address, and that IP address now enables me to formulate the IP packet that I want to send to the ultimate destination. So using DNS provides the usability to enable the use of IP, which is needed to communicate over the physical internet infrastructure of those multiple tier providers. Now, there's a new mechanism, or not really new, it's really been around for 10 years or so, but it's really just gaining traction in terms of implementation for securing DNS resolution called DNSSEC, or DNS Security Extensions. And what DNSSEC does, it does not encrypt DNS data, unlike what you may have heard. It actually just signs DNS data. It uses asymmetric cryptography, where a private key is used to sign resource record data in a zone, in a domain, and the public key is published with that information, and that is used to validate the signatures on that data as securely as having been published by that administrator, so that you don't have some attacker trying to impersonate a given domain name and providing falsified information to recursive servers, which again cache that information, so they're going to give this information out multiple times. So you want to make sure that cached information is accurate as possible. So the asymmetric cryptography provides data integrity and origin authentication, so I can determine if any data has been tampered with from how it's been published in the resource record as the administrator published it, as well as the origin authentication. Yes, that administrator published it because I've got their public key, and I can validate that. So if we kind of look at the process of resolution, we kind of follow this. We went through on the prior slide the whole top-down level to get to the example.com server. That still has to go on and transpire, but in this case I'm kind of skipping to the end where I'm giving back an answer saying it's 192.0.2.54, but it's been signed, and here I've got the corresponding public key that I use to sign that information. So through a series of validation of this key, I now need to say, okay, well, anybody can sign resource record data. They just need a private public key pair. Who's to say an attacker didn't just sign this? And here's the corresponding signature. The asymmetric cryptography just basically tells you that, yes, that public key goes with that signature for that data you received. So there's an added step that needs to be followed, and that's really to validate the key up the so-called chain of trust, which really mimics the same domain tree that we use to resolve information, except in the other direction, so to speak. So I need to ask the .com TLD server, hey, I got this public key from the example.com DNS server. Do you vouch for this? Is this what you have in your files? And it'll come back and say, yes, my DS, or delegation signer, information indicates that that key has been provided to me by the example.com provider, and I now hereby vouch for it. Here's a hash of that key, and by the way, here I'm signing this information, and here's my key. So that information is then used to likewise query the internet root server, and it too vouches for the .com information. It provides us that DS record. It signs that information, also provides its public key. The recursive server being configured with that public key as a trusted key, it can now check that key against its configuration, and yes, it all checks out, very good, and it passes the information back as a secure resolution. So the recursive server needs to be configured with those, with the public key of the root. And there is a mechanism to automatically adapt as changes are made on the internet root server. So that's recursive server is relatively straightforward to configure, but the signing of zones is a little more administratively intensive in terms of periodic maintenance that's required. However, the benefit is that your information is published securely. It's signed so that resolvers can be assured that it's published by you and that it hasn't been tampered with en route to your server. So what if there is no published answer for the query? So for example, if I issue a query for www record, typically the authoritative server, once you go down the domain tree, find the authoritative server, it's going to respond either here's the answer, or I'm authoritative for this, but there is no host by that name. And it'll come back with no data found, or NX domain as it's called. That's the name of the error message that comes back in the DNS message header. Or with bind 99, the latest version of the Internet System Consortium DNS reference implementation, they've implemented a redirect feature that enables you to define a redirect zone, a zone type that says, okay, if you get an NX domain back in one of your queries as the recursive server, just provide this IP address back. So maybe from an ISP perspective, they might use this feature to say, well, okay, here's the ISP search page. I'm gonna put you there because obviously you typed an address that doesn't exist. Maybe I'll give you some close hints or whatever that based on what you were looking for, whatever. It's really up to the ISP to program that page in, or that IP address that you want to send it to, and that just enables them to kind of redirect that information, that DNS query. It's only redirecting the DNS query, not in essence, I guess it's redirecting the traffic as well because it's providing the address back. But basically, it redirects you to a given IP address, and that's where a lot of times when you're using your browser and you get to maybe mistype in a web server address, you get to an ISP search page, and that's typically done through redirection. Now, if you are using DNSSEC, if you're attempting to requesting authenticated information with DNSSEC and the DNSSEC signs that information, it will not be redirected. So even if there is an NX domain, because DNSSEC provides authenticated denial of existence, that information will be passed through and that will not be redirected. So it does not break DNSSEC in that aspect. Now, DNSSEC is effective against the cache poisoning type of vulnerability. However, there are several other vulnerabilities that could impact DNS, and so we'll just highlight some additional security considerations you should consider or think about when thinking about securing your DNS infrastructure. First one is securing inter-server communication. So by that I mean when you configure a master server with an update to a resource record, for example, that information then gets zone transferred to the secondaries or the slaves serving that particular zone. So making sure that you've got ACLs, access control lists, in terms of who can do a zone transfer, and also TSIG keys, transaction signature keys, may be something you want to consider as well in terms of providing a signature on those zone transfers, on those updates, so that they are authenticated. So securing the inter-server communication so that you don't have an attacker trying to update your DNS server through an update process for lack of ACLs and TSIG keys. Securing the control channel. The RNDC command set, the remote name daemon control, really is a very powerful control channel for the bind DNS server implementation. So it allows you to reload a server, it allows you to basically stop accepting dynamic updates, you can basically stop the server. So it's very powerful, so it's something you want to consider maintaining control over. And likewise, as you can with inter-server communications, you can also control who can access that control channel remotely through ACLs as well as through keys, again for securing that authentication. Securing the server operating system. So there have been several vulnerabilities over the years in terms of smashing the stack and trying to infiltrate the server on which the DNS service is running. So protecting your operating system is one way to really protect against or mitigate that type of attack threat. And using hardened appliances is certainly one approach. There are several appliance vendors out there, of course, BT Diamond IP being among them. But other ways that you can, in your own hardware, if you've got your own hardening type of approach, that's certainly viable as well. So whether that means basically limiting the service, the server, to basically supporting the services running on it. So eliminating unnecessary services, parts of the file system, even ports that are open on the server. Those type of activities can be used to harden your server and protect the operating system. Also, keeping the operating system up to date is certainly another recommended work item that should be added to keeping your DNS server secure as well. And then server deployment and configuration. So really kind of a role-based approach is really recommended in terms of giving your server one thing to do in terms of either being a recursive server, so it's just responsible for accepting queries from your client community, your stub resolvers, and getting answers, and separating that from an authoritative server that basically is just responsible for answering questions. So it's not doing queries for anybody, it's just answering questions. And even within that, the authoritative side, having a hidden master, for example. And what that means is that I'm not publishing my master name server record in my parent zone. So in essence, coming down the domain tree to find my authoritative servers for my zones, I'm not basically publishing the name server as the master server. And really, the idea here is that you're not disclosing which server is the master or which among the set of NS records you publish could be the master, because once somebody knows who the master is, they know who to attack in terms of trying to do those updates and really falsify zone information. So hidden master is one approach that can be used to help secure your DNS infrastructure, separating the functions in terms of recursion, forwarding, root hints, also using views, and also logging. You definitely want to be checking your logs, just looking for any unusual activity that you may see from a traffic increase, whether it's a denial of a service type of attack. That is very important in general. And then lastly, just configuring your DNS server configurations, internet facing versus your internal. So, typically a lot of customers, you really dedicate servers to serve up external namespace. So their internet facing namespace. What are the servers I want to make available for internet users coming into my, my site off the web? And so you can restrict what gets published there, and then also, of course, control the updates of that information using the prior mechanisms we discussed. And then also, for your internal space, access to perhaps the same hosts that serve your external space, maybe running that on separate dedicated internal DNS servers, again, kind of separating the role and function of those for added security, and really kind of restricting who does what, so to speak, in the DNS infrastructure to limit any bleed over in terms of functionality and responsibilities. So hopefully this has given you a broad overview of DNS in general, and also DNSSEC, as well as highlighting some of the additional security considerations to think about for your DNS infrastructure. Thank you very much, and have a great day.